In the previous video, already we discussed the Affleck-Dine baryogenesis many times. So today I will revisit this topic again, how the Affleck-Dine builds the dynamicals over the cosmic history. So the Affleck-Dine build is motivated by the supersymmetry, because in the SUSY model, the scalar potential has the many Dirac directions. The scalar potential in the supersymmetry model can be decomposed in the F term and the D term part. The F term comes from the superpotential, but the D terms is generated from the gauge interaction. And the Dirac direction means that the D terms vanishes along the specific direction. So for the Dirac direction, the potentials exactly the zero. So if we choose the Beckham's expectation value of the scalar along the Dirac direction, then there is no energy to move this direction. But these Dirac directions can be lifted by the higher dimensional loop correction, but this correction will be very small, so that we can ignore at some moment. The simple example that we discussed in the many times ago is that just considering the two color field pi plus and pi minus with the opposite charges. Then the gauge interaction, the U1 gauge interaction gives the term as the difference between the pi plus chaos minus pi minus chaos. And the scalar potential is given by the chaos of this D term. So the Dirac directions conditions is given by the same Beckham's expectation value for the pi plus and the pi minus for the magnitude. So that we can make these broad directions with a specific continuous family. This is a very simplest example, but there are many different directions in the MSSM, because there are many scalar fields, fermions, and two Higgs double lab, and their charges are under the standard model gauges. So we can find the various Dirac directions by satisfying the gauge covariance term. For example, the like as HUHD or LLE, QRD, UDD. These are all the gauge invariant, and this color field can vanish for the specific condition. So over these Dirac directions, the Affleck-Dine dynamics can be discussed. So the Affleck-Dine field is introduced with the specific scalar field pi. This Affleck-Dine field, briefly the AD field, carries the baryon on the left number. And along these Dirac directions, the potential values are unchanged, so the pi can have the very large Beckham's expectation values in the early universe, and it ensures that the enough baryon asymmetry generations. The asymmetry generation, especially the CP violating terms, comes from the phase term of this complex AD field. So we can relate this complex color AD field pi with the radial component and angular component. And this complex fields rotates over the plane, the complex plane, and this coherent rotations in the Beer space eventually make the generate asymmetry generation. So if we consider that the global U1, for example, the U1b or U1l, or the baryon or lepton number, then we can find the noidal current corresponding to this global symmetry, noidal current for the J mu. And by integrating this noidal current, we can obtain the charge density MB. And this corresponds to the imaginary part of the pi star and the pi dot. So the baryon number density comes from this imaginary part, and if we calculate it with the radial path and angular path, this is just simply given by the dot of the status. It means that the rotational dynamics gives the asymmetry generation. And the produces asymmetries that transfer to the standard model sectors by the decay of the AD field. So now let's turn to the how the AD field dynamics is given. This AD field got some specific form of the potential, especially that there will be the corrections from the cosmological and the thermal one. The first one is the Hubble-induced one. The supergravity in the supersymmetric model gives the F term coming from the Hubble term. So this equation corresponds to the Bose-Friedman equation. And the energy density is given by the potential dominant one, and this scalar potential comes from the F term. So we can find that the the F scales over the M Planck gives the Hubble scale, and we can find this relation first, and the AD field pi is coupled to the inflaton through the Planck surplus. So this is just the supergravity coupling in the Carl potential. Carl potential means that there is the conjugate of the superfield is inside in the potential, unlike the superpotential. So the Carl potential helps this conjugate field, but the superpotential only consists by the just the superfield. There is no conjugate in here, and by calculating the quadratic term of the scalar potential, then we can obtain the Fi squared over the M Planck, because the quadratic term means that this pi square terms differentiate out. So there's just a remaining term with the I squared over the M Planck squared, and by the dimensional analysis, the remaining term is just like pi squared. And by using the relation, we can obtain the Hubble term. So the points of this part is the from the supergravity effect, is the AD field pi get the some Hubble-induced mass term. So in the quadratic term, there will be the Hubble-induced term here. And similarly, for the A term, also there is the Hubble-induced term. So the first part corresponds to the mass term of the AD field. M scale is the soft mass for the SUSY breaking. This H is the Hubble-induced mass term. And the second part is the F term contributions from the superpotential with all the higher dimensional operator. And in the second line, the binary terms correspond to the A term, The former ones is the Hubble-induced item, but the second term is just the soft surge breaking atom with also all the higher dimensional operator contributions that is included. And this surge breaking, the soft term, becomes important when the Hubble terms and the soft term becomes comparable. And some higher dimensional operators, non-normalizable ones, leaves the blood directions. And A term is usually the complex number, so that it contains the phase which violates the CP and also the B or lepton number. So this is a typical form of the AD field. This is consisted by the mass term, up term contribution, A term, and some terms that comes from the Hubble. So under this AD field potential, we can describe the dynamics of the AD field. The important characteristic of the AD field, A, it got the coherent oscillations around its minimum of the potential, and B, it has rotations all over the complex plane. First of all, the Hubble indices of the mass term makes the origin of the potential is unstable during the inflation, because this CH's coefficient is usually given by the positive, so this makes the unstable potential. So the pi goes to the very large vacuum expectation value when this Hubble mass term is the large compared to the just the bare mass term. And in this case, when the Hubble in this system is very large, the scale is roughly given by the this form. So we can compare the Hubble term and higher dimensional operator. Then the scale is just given by the following form. But when the Hubble lies drop below the soft mass, then the sign of the quadratic terms changes. So now the potential becomes the bounded below. So the AD field starts the coherent oscillation around the minimum of the potential. So that we get the burst characteristic coherent oscillation. But this large Hubble in this system in the early universe ensure that the earlier values of the AD field is extremely large. So in the complex plane, the AD field starts the very large magnitude. And the next characteristic of the dynamics for the AD fields is AD fields rotates over the complex plane. These rotations comes from the atom. This atom has the CP violating phases, and this kick the angular part of the AD field, the status. So let's write the atom contribution of the potential. Here the atom, and also the atom can be decomposed in the radial part and the angular part. Again, there is a radial part and the angular part, and also the AD fields already decomposed by the radial part and angular part. So here is the radial part and this is the angular part. And if we differentiate the potential, we can obtain this. And this contribution from the potential will insert it in the action. And by assuming that the AD field is the coherent, spatially homogeneous, then only the remaining term is the time derivative. Then just the Lagrangian is given by the following simple form, just the time derivatives for the radial and the angular part. And we can define the angular momentum, especially including the scale factors. And if we find the equation of the motion by using the Euler-Lagrange equation, then the changes of this co-moving angular momentum is given by the derivatives of the potentials about the status. So the non-zero of the right-hand side, the both derivatives of the potentials gives the changes of the angular momentum, which means that the rotations start. And this rotation require that the item and already we watched that the AD field potential get the two distinguishes items. The first one is Hubble indices, and the second one is just a substem. And these two terms are different phases. And when the Hubble terms are comparable to the substem, then the phase difference becomes important. And ADP will start the coherent oscillation, and the Hubbles are comparable to the AD field mass. And when the Hubble terms are drop down the soft mass term, then the dominant atoms are changes, and this shifts the effective phases of the item. So originally the Hubble terms are dominated, but now the subterms are dominated. And this changes of the phase makes the big difference between the initial setups and the final setup. So this generates the non-zero torque and making the rotations over the complex plane of the pi. So the point is the AD field get the rotation behavior. The importance laws comes from the Hubble-induced system, which ensure that the large field value and also the item makes the rotations with the different phases between the Hubble term and the soft term. Now we know that the asymmetries are generated by the rotation. Already we saw the Noether current correspond to the U1 and corresponding to the generated asymmetries comes from the rotation path theta dot here. So this Noether current is important. And we can find the equation for the number density of the baryon and B by using the equation of the motion. This is the equation of the motion, just a simple one. And if we derivatives the Noether current and inserting the equation of the motion here, and the time component of the Noether current is just a baryon number density, so that we can obtain the EOM for the baryon number density. And the right hand side is given by the atom, Hubble and the soft one. And by solving this equation, we can obtain the final value of the MB and the final values of the MB. And our desire is Affleck-Dine bioanalysis can explain the baryon asymmetry, so we can calculate this. So the baryon to the antiplatelets are defined by the MB over the S. And there should be the corrections because the baryogenesis moment and the BAE moment is different. The generations of the baryon asymmetries, so when the ADP starts the oscillation and the rotation when Hubble is comparable to the ADP mass. So this moment is the oscillation time. But there are also different moments, the leading moment. So because in the denominators for this YB entropy densities that comes from the leading temperatures. So that is just realize the final factors, the oscillation time and the leading time. So why the leading time is important? Because entropy densities are determined after the leading. And this leading moment, scale factors at the leading moment, is determined by the leading temperatures with the following process. So the final baryon to the entropy is that determined by the leading temperature and the build value of the AD field when the oscillation start. And also the mass of the AD field. The epsilon contains the how much the baryon asymmetries are generated during the rotation. This is just the efficient factors and can be determined by the solving the EOM for the baryon number density MB. So today we talk about the dynamics describes the Affleck-Dine field. The AD potentials that contains the soft mass term and item, and especially the Hubble-induced one. And the baryon number densities are generated by the rotations of the AD field, and this rotation can be ensured by the atom. Also, the Hubble-induced system guarantees that the field value becomes very large in the initial condition. And the generated asymmetries in the AD field eventually transfer to the standard model factor. The typical example of the AD fields is given by the compositions of the several Clark, Lupton, and the Higgs field. So today we talk about the Affleck-Dine baryogenesis, how the AD fields behaves over the cosmic history. But this is just a revisit of the previous video.